Good morning, everyone. Heartfelt gratitude to Flaps. Dear all participants and panelists, my warm welcome. I am happy to be part of this beautiful platform for the researchers across the world. My name is Sachin Rahi, presently affiliated with Department of Electrical Engineering, and I am pursuing PhD under supervision of Dr. Shree Tiwari. Today I am going to give presentation on topic effect of annealing on low voltage organic field effect transistors with PVDF-TrFE gate dielectric. My paper ID is 6087. So this is the outline of my presentation that I will be going through as my presentation progresses. First of all, I'll discuss introduction in which I'll discuss TIPS-Pentacene as organic semiconductor and PVDF-TrFE as a gate dielectric. Next, I'll discuss fabrication and characterization of OFET. After that, I'll discuss electrical characteristic of OFET devices, then operational stability analysis, then effect of annealing on OFET. At last, I'll discuss summary and future work. So I begin with the question, why there is search for organic electronics? Answer to this question is that because organic electronics is an emerging field of electronics in which various organic materials such as dielectric, conductor, semiconductor polymers, or small organic molecules are used for device fabrication. Organic materials possess several advantages like low cost, lightweight, flexibility, process simplicity like solution process, low temperature processing like devices are fabricated at low temperature. This is the basic structure of TIPS-Pentacene. Reason behind using this is solution process, high air stability, low cost. In this study, we are using TIPS-Pentacene blend with polystyrene. We blending polystyrene because polystyrene is providing smoother surface with drastically reduced charge trapping, also improved performance and stability. There is a vertical phase separation between TIPS-Pentacene and polystyrene. Uniform and intimate dielectric semiconductor interface we are getting from this. PVDF-TrFE as a gate dielectric. PVDF-TrFE is broadly used as a dielectric layer for OFET. The motivation behind choosing PVDF-TrFE as gate dielectric is because of numerous advantages: high thermal stability, low power consumption, good mechanical properties, transparency, chemical resistance, high dielectric strength, which helps in reducing leakage in the device. There are also challenges associated with PVDF-TrFE based OFET like high operating voltage 30 to 100 volt, low mobility, poor performance, higher surface roughness, parasitic effect, charge trapping. Due to higher surface roughness, charge trapping takes place, which leads to high operating voltage from 30 to 100 volt. Next, I will discuss fabrication of OFET. First of all, I'll take ITO glass as a substrate. On the top of it, I'll deposit PVDF-TrFE, and on the above of it, this pentacene and PS crystal drop casted. And at last, thermally deposited gold as a metal contact. For making it, first of all, I clean ITO coated glass substrate. Then PVDF powder was dissolved in DMF with 15 weight% and the solution was prepared by stirring for 12 hours at 35 degrees Celsius. The PVDF layer is obtained by spin coated at 2000 RPM for 30 seconds. Then the film was annealed at 90 degrees Celsius for 2 hours. The solution of 0.58% is pentacene and 0.58% PS is blended at 1:1 ratio and drop casted at room temperature. Finally, AU top electrodes are deposited as the source and drain contact. These are the electrical characteristics of my fabricated OFET device. These transfer and output characteristics clearly shows that the device shows p-type behavior. From these output and transfer characteristics, we are able to extract various parameters like mobility, mobility which is 0.4, maximum mobility 0.6, threshold voltage minus 0.2, current on-off ratio 10 to power 4, sub-threshold swing is 0.4, interface step density is 2 into 10 to power 11. Solution process PVDF-TrFE based OFET operated at minus 5 volt demonstrated high performance. PVDF-TrFE is emerged as a suitable dielectric for flexible OFETs. Operational stability analysis. In this, multiple scan of transfer characteristic up to 100 cycle will be conducted, and it is seen that there is the overlapping in the transfer characteristic. In figure B, the figure B is extracted from figure A, in which it is shows that threshold voltage shows minimal variation and ion is also shown minimal variation. Figure C, on applying bias stress for a device up to 5400 seconds, there is a 2% decay in the current, which resembles that this device is highly operational stable. Effect of annealing on OFET. Initially, at low annealing temperature, device performance was similar to pristine case, as you can clearly see from figure A. With increase in annealing temperature above 50 degrees Celsius, resulting in the deterioration in the performance of the device. As you can see in the figure A, when I increase the temperature above 50 degrees Celsius, the current got decreased. From figure 2 is extracted from figure A, in which the ion is decreases as the temperature increases, and there is the shift in the threshold voltage. This study is also concluded by optical image of the semiconductor surface of pristine and annealed at various temperatures. Here, the micro cracks are generated in the active layer at the temperature 70 degrees Celsius and 100 degrees Celsius. Thus these generated micro cracks in the active layer film increases the stress, which eventually leads to deterioration in the performance. OFETs with TIPS-Pentacene PS as active layer and PVDF-TrFE as a gate dielectric are demonstrated. Fabricated device exhibited smooth electrical characteristic with average field effect mobility 0.4 centimeter square per volt per second near zero threshold voltage and high on-off ratio of 10 to power 4 at an operating voltage of minus 5 volt. A very high stability under bias stress and high repeatability upon multiple scan of transfer characteristic up to 100 cycles were achieved. A deterioration in the performance of OFET was observed upon annealing at temperature over 50 degrees Celsius. Implementation of these fabricated device on flexible substrate and utilization for detection of physiological changes like pressure and temperature in the human body will be the future direction. I would like to acknowledge Science and Engineering Research Board, Department of Science and Technology, India, and Visvesvaraya YFRF Project, Ministry of Electronics and IT, India, for providing us financial support. Thanks for watching my presentation. It's my pleasure to be part of this conference. Thank you.